Touch the wall beside you. Feel its solidity, its texture, its absolute there-ness. Press your palm against it and feel the resistance, the way it refuses to yield, the undeniable boundary between your hand and the surface. This wall is real. Your hand is real. The sensation of contact, the pressure on your skin, the coolness or warmth of the material, all of it is completely, utterly real. Now close your eyes and focus on that sensation. The wall pushes back against your hand with exactly the force you apply to it. Atoms in your skin, separated from atoms in the wall by distances that are mostly empty space, somehow create this experience of solid contact. The electromagnetic forces between electrons in your hand and electrons in the wall generate the feeling of impenetrability, of substance, of realness. But what if I told you something strange? What if this wall, your hand, the space between them, the room around you, your body, your thoughts, the entire three-dimensional universe you inhabit, might be a projection? Not a projection in the sense of a movie on a screen, not an illusion or a trick, but a genuine physical projection from information encoded on a distant two-dimensional surface, like a hologram emerging from a flat boundary. What if the depth you perceive, the distances you measure, the three dimensions of space you move through, are not the fundamental reality, but rather an emergent phenomenon, a way of organizing information that is actually stored somewhere else, on a boundary far away, encoded in a form that has no depth at all? This is not science fiction. This is not mysticism or philosophy masquerading as physics. This is a serious proposal emerging from some of the deepest and most carefully worked out mathematics and theoretical physics, a principle called the Holographic Principle, which suggests that our three-dimensional universe, with all its depth and volume and space, might be entirely equivalent to a two-dimensional description, a projection from a cosmic boundary. Let that idea rest gently in your mind for a moment. Do not try to grasp it fully yet. Do not try to visualize it or make complete sense of it. Simply let it sit there, this strange possibility that reality as you know it might be something very different from what it appears to be. There is no urgency here. We have time to explore this slowly, carefully, letting each piece of understanding settle before moving to the next. The holographic principle does not say that the world is fake or unreal. It does not diminish the reality of your experience. The wall is still solid. Your hand still feels it. The sensations are genuine. What the holographic principle suggests is that there are two equally valid ways to describe reality, two complete descriptions that give the same predictions for every observation you could ever make. One description uses three dimensions of space plus time, the familiar world of depth and distance. The other uses two dimensions of space plus time, a description where information is encoded on a boundary surface. These two descriptions are mathematically equivalent. They are not approximations of each other. They are exact translations, like two languages that express precisely the same meaning with different words. Every event in the three-dimensional description has a corresponding event in the two-dimensional description. Every measurement, every interaction, every physical law is preserved in the translation. The question of which description is more fundamental, which one is the real reality, might not even be a meaningful question. They are both real. They are both complete. They are two ways of expressing the same underlying truth. As you settle into comfort, as your breathing slows and your body relaxes, let us begin this journey into one of the strangest and most beautiful ideas in modern physics. We will start with something familiar, with holograms as you may already know them, those shimmering three-dimensional images that seem to float in space. Then we will move deeper, exploring how black holes reveal the profound mystery about information and reality. We will follow the trail of clues that led physicists to propose the holographic principle, and we will try to understand what it might mean for the nature of space, time, and existence itself. This is not a journey that leads to fear or uncertainty. It is a journey that leads to wonder, to a deeper appreciation of how strange and how beautiful the universe truly is. And along the way, as concepts accumulate and build upon each other, you might find your everyday concerns growing quieter, more distant, as your mind focuses on these vast cosmic questions that put all human worries into a different perspective. So breathe slowly, let your thoughts drift, and let us explore together the possibility that you, me, everything we call reality, might be a hologram, a projection from the boundary of the universe, playing out in 3 dimensions even though the fundamental information exists in 2. To understand the holographic principle, we must first understand what a hologram actually is. Most people have seen holograms in daily life, perhaps on credit cards or identification documents, where a flat surface displays an image that seems to have depth, that changes as you tilt it, that looks 3-dimensional even though it is printed on something completely flat. But let us go deeper into how holograms actually work, because the physics of holography contains the seed of a much larger idea. A hologram is not simply a 3-dimensional picture. It is a way of encoding complete 3-dimensional information onto a 2-dimensional surface. The process reveals something profound about how information can be stored and represented. Imagine you want to record an image of an object, let us say an apple, in a way that captures not just how it looks from one angle, but how it appears from every angle, with full depth information. A photograph cannot do this. A photograph is a projection, yes, but it is a lossy projection. It captures light from the apple as seen from one specific viewpoint, and the depth information is lost. You cannot move your head and see the other side of the apple in a photograph. A hologram, however, captures something more complete. It records the interference pattern created when light from the object meets a reference beam of light. This interference pattern, when recorded on a flat surface, contains enough information to reconstruct the entire 3-dimensional light field that was coming from the object. When you illuminate the hologram with the right kind of light, it reproduces that light field, and your eyes see a 3-dimensional image hanging in space, an image you can view from different angles, an image with genuine depth. Here is what makes this remarkable. The hologram is flat. It is 2-dimensional, but it contains the complete 3-dimensional information. Every point on the holographic surface contributes to the entire 3-dimensional image. If you cut a hologram in half, you do not get half the image. You get the whole image, though perhaps fuzzier, viewed from a narrower range of angles. The information is distributed across the surface in a way that is fundamentally different from how information is stored in a photograph. This property is called redundancy or non-locality. The 3-dimensional information is encoded across the 2-dimensional surface in such a way that each part of the surface contains information about the whole 3-dimensional scene. Damage one part of the hologram, and you lose some resolution, some clarity, but not a specific chunk of the image. The information is smeared out, distributed, encoded in the interference pattern across the entire surface. Now, you might think this is just a curious property of a particular way of recording images, an interesting technical trick used in security features and science museums. But what physicists discovered, starting in the 1970s and becoming increasingly clear through the 1990s and into the present century, is that this might be how the universe itself works. Not as a metaphor, not an analogy, but as a precise mathematical truth. The suggestion is that our 3-dimensional space, with all its volume and depth, might be like the 3-dimensional image in a hologram, and that the complete information about everything in this space might actually be encoded on a 2-dimensional boundary surface, perhaps at the edge of the observable universe, or perhaps on the surfaces of black holes, or perhaps in some other way we do not yet fully understand. This idea did not come from philosophical speculation. It emerged from trying to solve a very specific problem in physics, a problem involving black holes and the nature of information. To understand how we arrived at the holographic principle, we need to follow the trail of this problem, starting with a discovery made by Stephen Hawking in the 1970s that revealed a deep conflict between two of our most successful theories of physics. Let us take our time with this. Let the concept settle gently. We are building a structure of understanding, layer by layer, and each layer needs to be solid before we add the next. There is no rush. We have all the time we need to explore these ideas as they deserve to be explored, with patience and care and a sense of wonder at how the universe reveals its secrets to those who look closely enough. Black holes are among the strangest objects in the universe, and we have explored them before in another journey. They are regions where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. Everything that falls into a black hole disappears from the observable universe, crossing that one-way threshold into a region from which no information can return. For a long time, physicists thought this was the end of the story. Matter falls in, information is lost, the black hole grows. The black hole was thought to be the simplest possible object in physics, characterized by just three numbers: its mass, its electric charge, and how fast it is spinning. No matter what falls into a black hole, whether it is a star, a planet, a library full of books, or a computer full of data, once it crosses the event horizon, all the detailed information about what it was is lost. The black hole remembers only the total mass, charge, and angular momentum that was added. This property was summarized in a phrase coined by John Wheeler. Black holes have no hair, meaning they have no extra features, no complexity beyond those three basic numbers. But in 1974, Stephen Hawking made a discovery that changed everything. Using quantum field theory, the physics of quantum mechanics applied to fields that permeate space, Hawking showed that black holes are not entirely black. They emit radiation, now called Hawking radiation, a faint glow of particles that slowly causes the black hole to lose mass and energy over immense spans of time. This discovery was profound for many reasons, but it created a serious problem, a paradox that has driven much of theoretical physics for the past 50 years. The problem is this: Hawking radiation appears to be random. It carries energy away from the black hole, but it does not seem to carry information about what fell into the black hole. If you could collect all the Hawking radiation emitted over the trillions upon trillions of years it takes for a black hole to evaporate completely, and if you analyzed that radiation in perfect detail, you would not be able to reconstruct what had fallen in. The radiation is thermal, random, containing no memory of the books, the computers, the organized matter that was consumed. This is a problem because quantum mechanics, one of the two foundational theories of modern physics, insists that information cannot be destroyed. This principle is called unitarity. In quantum mechanics, the state of a system evolves according to equations that are reversible. If you know the state now, you can calculate the state in the future. And crucially, if you know the state in the future, you can calculate the state in the past. Information is conserved. Nothing is truly lost. But black holes, according to Hawking's calculation, appear to destroy information. Matter with complex quantum states falls in. Random thermal radiation comes out. The information about the initial state is lost, seemingly destroyed when the black hole eventually evaporates completely. This contradiction between general relativity, the theory that describes black holes, and quantum mechanics, the theory that describes information conservation, is called the black hole information paradox. For decades, physicists debated this. Some argued that information really is destroyed in black holes, that quantum mechanics needs to be modified. Others argued that the information must somehow be preserved, that we are missing something about how black holes work. Hawking himself initially believed information was lost, but later changed his mind after further developments in the field. The key insight that began to resolve this paradox, or at least point toward a resolution, came from considering not just the radiation, but the entropy of black holes. Entropy is a measure of disorder, or more precisely, a measure of the number of possible microscopic states that correspond to a given macroscopic state. The higher the entropy, the more hidden information there is, the more microscopic details that are not visible in the large-scale description. In the 1970s, Jacob Bekenstein and Stephen Hawking derived a formula for the entropy of a black hole. This formula is remarkably simple. The entropy of a black hole is proportional to the area of its event horizon, not to its volume. This is strange. For ordinary objects, entropy is proportional to volume. A larger box of gas has more entropy than a smaller box, assuming the same temperature and density. But for black holes, it is the surface area that matters. The Bekenstein-Hawking entropy formula says that the entropy S of a black hole equals a divided by 4, where A is the area of the event horizon measured in Planck units. The Planck length is about 10 to the negative 35 meters, an incredibly tiny distance where quantum effects on spacetime itself become important. So the formula is telling us that the event horizon can be thought of as being divided into tiny Planck-sized pixels, and each pixel encodes a certain amount of information, about 1 bit per pixel. This is strange and suggestive. If the entropy is proportional to area, and entropy measures information, then perhaps the information about everything inside the black hole is somehow encoded on its surface, on the event horizon itself, not stored in the three-dimensional volume, but on the two-dimensional boundary. Think about that for a moment. When you throw a book into a black hole, all the information in that book, the words, the ideas, the patterns of ink on paper, falls toward the singularity at the center. But according to this idea, the information does not disappear. Instead, it is scrambled and encoded on the event horizon, spread out across the surface in a way that preserves the total information content even though the details are no longer accessible in any obvious form. This was the first hint of holography in physics. The three-dimensional interior of a black hole might be entirely described by information on its two-dimensional boundary. The volume and the surface are not separate things. They are two equivalent descriptions of the same physical reality. But this was just a hint, a suggestive clue. To turn it into a precise principle required more work, more insights, and a deeper understanding of how quantum gravity, the theory that unites quantum mechanics and general relativity, actually works. And that understanding came from an unexpected place, from studying not black holes in our universe, but certain theoretical universes with unusual properties, spaces that exist primarily in the equations of physicists, but that reveal profound truths about the nature of reality. Let your mind rest here for a moment. We have introduced several deep ideas. Holograms as a way of encoding three-dimensional information on two-dimensional surfaces, black holes as objects that seem to destroy information, the paradox this creates for quantum mechanics, and the strange discovery that black hole entropy depends on surface area rather than volume. These pieces are beginning to fit together, but the picture is not yet complete. We need to explore how physicists took these clues and constructed a full principle, a statement about how information in any region of space might be encoded on the boundary of that region. This is where we turn next to the work of Gerard T. Hooft and Leonard Susskind in the 1990s, and to the revolutionary discovery by Juan Meldacena in 1997 that gave the holographic principle a rigorous mathematical foundation. But first, let yourself absorb what we have covered. The wall beside you, solid and real, might be described completely by information encoded elsewhere. The three-dimensional space you inhabit might be a projection. Black holes, those ultimate destroyers, might actually preserve everything on their surfaces. And information, that abstract concept, might be the most fundamental thing in the universe, more basic than matter, more basic than energy, more basic even than space itself. These are not small ideas. They reshape how we think about existence. And as they settle into your mind, you might notice that your sense of solid ground is shifting slightly, not in a frightening way, but in a way that opens up new possibilities, new ways of understanding what it means to be here, to exist, to experience this apparently three-dimensional reality. Breathe, rest in the strangeness, and let us continue. In the early 1990s, two physicists working independently came to a similar radical conclusion. Gerard T. Hooft, a Dutch Nobel laureate, and Leonard Susskind, an American theoretical physicist, both proposed that the information content of any region of space is not proportional to its volume, as you might expect, but to the area of the boundary surrounding that region. This proposal, which they called the Holographic Principle, was inspired directly by the properties of black hole entropy, but was meant to apply much more broadly to all of space, not just to black holes. The holographic principle makes a precise claim. Take any region of space, any volume you want to consider. Draw a boundary around it, a two-dimensional surface that encloses the region completely. According to the holographic principle, all the information about what is happening inside that volume, every particle, every field, every physical process, can be encoded on the boundary surface. Furthermore, there is a limit to how much information can be contained in that region, and this limit is determined by the area of the boundary, not the volume it encloses. This limit is called the Bekenstein bound, named after Jacob Bekenstein, who first derived it in the context of black holes. The bound says that the maximum entropy, the maximum information content, of a region is proportional to the area of its boundary measured in Planck units. Specifically, the maximum number of bits of information that can be contained in a region is approximately equal to the area of the boundary divided by 4 times the square of the Planck length. To get a sense of what this means, consider a sphere 1 meter in radius. Its surface area is about 12 square meters. In Planck units, which are incredibly tiny, this area corresponds to an enormous number, about 10 to the 70 Planck areas. According to the Bekenstein bound, this sphere can contain at most about 10 to the 70 bits of information. That is a huge number, far more information than is contained in all the computers and books and brains on Earth combined. But here is the key point. This limit depends on the surface area, not the volume. If you double the radius of the sphere, the volume increases by a factor of 8, but the surface area only increases by a factor of 4, and so the maximum information increases by a factor of 4, not 8. For ordinary matter, information content is proportional to volume. A larger box can hold more books. But according to the holographic principle, when you push toward the maximum possible information density, when you approach the fundamental limits of what space can contain, it is the surface that matters, not the volume. This is deeply counterintuitive. Our everyday experience tells us that information is stored in 3-dimensional volumes. A hard drive has depth. A brain has volume. Books fill shelves that occupy space. How can it be that fundamentally, the information is really on a boundary? The answer, T. Hooft and Susskind suggested, is that 3-dimensional space itself might be a kind of illusion, or more precisely, an emergent phenomenon. The fundamental description of physics might be a 2-dimensional theory living on a boundary surface, and the 3-dimensional world we experience is a holographic projection from that boundary. Just as a hologram creates a 3-dimensional image from a 2-dimensional surface, the universe might create the appearance of 3-dimensional space from information encoded in 2 dimensions. This was a bold proposal, but it remained somewhat speculative until 1997, when Juan Meldacena, a young physicist working at Harvard, made a breakthrough that gave the holographic principle a concrete mathematical realization. Meldesena discovered a precise correspondence between two theories that had previously seemed completely unrelated. His discovery is called the AD-CFT correspondence, and it is one of the most important developments in theoretical physics in the past few decades. Let us take this slowly, because the details matter, but also because the ideas are subtle and deserve careful attention. AD stands for anti-de Sitter space, a particular kind of space-time geometry that appears in Einstein's theory of general relativity. It is not the geometry of our actual universe, but a theoretical space that physicists study because it has nice mathematical properties that make calculations possible. Anti-de Sitter space has a peculiar feature. It has a boundary, a kind of edge at infinity, and this boundary is one dimension lower than the interior. If the interior has 3 dimensions of space plus 1 of time, the boundary has 2 dimensions of space plus 1 of time. The boundary is infinitely far away in a certain sense, but it still encloses the interior completely. CFT stands for conformal field theory, a particular kind of quantum field theory without gravity that lives in a flat space-time, a theory of particles and fields obeying quantum mechanics, but not general relativity. Conformal field theories have special symmetries that make them mathematically tractable, and they are used throughout physics to describe critical phenomena and other interesting systems. What Meldesena showed is that a specific theory of gravity in anti-de Sitter space, including all the complications of general relativity, quantum fields, black holes, the full machinery of physics in a 3-dimensional space, is exactly equivalent to a conformal field theory living on the 2-dimensional boundary of that space. Not approximately equivalent, not similar, exactly the same. Every calculation you do in the gravitational theory has a corresponding calculation in the boundary theory that gives the same answer. This is astonishing. You have a universe with gravity, with 3 dimensions of space, with all the richness that comes from general relativity and quantum mechanics. And it turns out that this entire universe is equivalent to a theory without gravity, living in 2 dimensions on the boundary. The 3-dimensional space, the depth, the volume, all of it emerges from the 2-dimensional theory. The interior is a hologram. Meldesena's discovery was not a proof that our universe is a hologram. The AD space he studied has different properties from our actual universe. Our space is expanding, and it does not have the kind of boundary that AD space has. But what Meldesena showed is that holography is not just a vague idea or a philosophical speculation. It is a precise mathematical reality in at least some contexts. There exist pairs of theories where one lives in a higher dimensional space with gravity and the other lives in a lower dimensional space without gravity, and these 2 theories are exactly equivalent. They are 2 languages describing the same reality. This equivalence has been tested in countless ways over the past 25 years. Physicists compute complicated properties of black holes in the gravitational theory and find that the same properties emerge from calculations in the boundary theory. Processes that seem completely different in the 2 descriptions turn out to give identical results. The correspondence is not just qualitative. It is quantitative, precise, trustworthy. What does this mean? At the very least, it means that space, as we normally think of it, is not fundamental. In the boundary theory, there is no 3rd dimension. There is no depth, no interior. Space is 2-dimensional. Yet the boundary theory contains all the information needed to describe everything happening in the 3-dimensional space, including the geometry of space itself. The 3rd dimension is not an input. It is an output. It emerges from the quantum entanglement and interactions of the fields on the boundary. This is where the holographic principle moves from being a curious idea about black holes to being a profound statement about the nature of reality. If space itself can emerge from a lower dimensional description, then our intuition about what is fundamental needs to change. We think of objects as existing in space, as occupying locations, as separated by distances. But perhaps space is not the container in which things happen. Perhaps space is a way of organizing information, a convenient description that emerges from more fundamental structures that are not spatial at all. Let that thought rest gently. You do not need to fully grasp it yet. The idea that space itself is emergent, that the distances and volumes we measure are not fundamental but arise from something deeper, is strange enough that it takes time to absorb. But this is where modern physics is pointing, toward a universe where information is primary and space is secondary, where the geometry we experience is a holographic projection from a boundary that might not even be localized in the way we think of locations. As we continue this exploration, we will look at what this means for time, for consciousness, for the nature of existence itself. But first, let these ideas settle. The holographic principle is real. It is not science fiction. It is mathematics. And it suggests that the three-dimensional world you move through, including your own body, might be a projection from information encoded elsewhere, on a two-dimensional surface that is, in some sense, the true fundamental description of reality. Now that we have established the mathematical reality of holography through the AD-CFT correspondence, we can begin to explore what this means for the nature of space and time themselves. If a three-dimensional universe with gravity can be completely equivalent to a two-dimensional theory without gravity, and if all the information about the interior is encoded on the boundary, then our understanding of what space is must change fundamentally. In our everyday experience, space is a container, a background in which events occur. Objects are located at positions in space. They are separated by distances. When something moves, it travels through space from one location to another. Space seems absolute, fundamental, prior to the things that exist within it. This is the view that Isaac Newton held, the idea of absolute space as an unchanging stage on which the drama of physics plays out. Einstein modified this view with general relativity, showing that space is not absolute but dynamic, that it can curve and stretch and ripple in response to matter and energy. Space-time, the unification of space and time into a single four-dimensional entity, is not a static background, but an active participant in physics, affecting and being affected by everything within it. Yet, even in general relativity, space-time is still viewed as fundamental. It is the arena, the field on which the equations are written. The holographic principle suggests something more radical. It suggests that space-time, including the dimension of depth, might not be fundamental at all. Instead, space-time might be emergent, arising from more basic structures that are not themselves spatial. Just as temperature emerges from the motion of molecules and pressure emerges from countless collisions, space itself might emerge from the quantum entanglement and interactions of more fundamental degrees of freedom that are not located anywhere, because location is a concept that only makes sense after space has emerged. Let us think carefully about what emergence means. Temperature is a useful concept, but there is no such thing as the temperature of a single molecule. Temperature is a property of a collection, an average over many particles. Similarly, space might be a useful concept that describes collective properties of more fundamental entities, but those entities themselves might not exist in space. What could these more fundamental entities be? In the AD-CFT correspondence, they are quantum fields on the boundary. These fields have values at every point on the two-dimensional boundary, and they interact with each other according to the rules of quantum field theory. When you solve the equations for these fields, when you calculate how they evolve and interact, patterns emerge. And encoded in those patterns is the entire geometry of the three-dimensional space, including how it curves, how it contains black holes, how particles move through it, everything. The geometry of the three-dimensional space is not put in by hand. It is not an assumption. It is a prediction, a result of the calculation. You start with a two-dimensional theory, and out comes a three-dimensional space. The third dimension, the depth that seems so real and tangible, is emergent. Now, our universe is not exactly like Ad space. Our space is not negatively curved in the way Ad space is, and it does not have the kind of boundary that Ad space has. But many physicists believe that a similar principle applies. There are proposals that our universe might be holographic in a different way, perhaps with the boundary being the cosmological horizon, the edge of the observable universe, or perhaps with holography applying in a more subtle manner that has not yet been fully worked out. One intriguing possibility involves the cosmological horizon, because our universe is expanding, and because that expansion is accelerating due to dark energy, there is a distance beyond which we can never receive signals. Light from beyond the cosmological horizon will never reach us, no matter how long we wait, because the expansion carries those distant regions away faster than light can traverse the growing distance. This horizon is a real boundary, a surface that divides the observable universe from the unobservable. Some physicists have proposed that this cosmological horizon might function as a holographic screen, a two-dimensional surface on which all the information about the interior of the observable universe is encoded. If this is true, then everything we observe, every star, every galaxy, every event in cosmic history, corresponds to information on this distant boundary. The boundary is perhaps 100 billion light years away, receding from us as space expands, but in a holographic description, it is where the information actually resides. This is dizzying to contemplate. You are here, reading these words, feeling the weight of your body, aware of the space around you. And yet, according to this principle, all the information that defines you, your thoughts, your memories, the atoms of your body, might be encoded on a surface billions of light years away, not as a copy, but as the fundamental description. The you that exists here in three dimensions is the hologram. The information on the boundary is the original. But immediately, we must be careful with language. Words like original and copy imply that one is more real than the other, and that is not what the holographic principle says. Both descriptions are complete. Both are valid. Both are real. The three-dimensional description and the two-dimensional description are two ways of talking about the same reality, and neither is more fundamental than the other, or perhaps both are equally fundamental, which amounts to the same thing. This equivalence is important to understand. When we say the universe might be a hologram, we are not saying it is fake or illusory. We are saying that there exists a precise mathematical correspondence between a description with three spatial dimensions and a description with two spatial dimensions. And these two descriptions give identical predictions for everything you can measure. The question of which one is really real is not a question physics can answer, and perhaps it is not even a meaningful question. What about time? Time also behaves strangely in holographic theories. In the AD-CFT correspondence, time in the interior three-dimensional space corresponds to time on the boundary, but the relationship is not always straightforward. In some cases, what we experience as the flow of time might also be emergent, arising from correlations in the boundary theory rather than being fundamental. Some researchers have explored the idea that time itself, like space, is not a basic ingredient of reality, but rather an emergent concept that arises from more fundamental structures. At the deepest level, there might be no time, no before and after, only relationships between different states of a timeless system. The flow of time, the sensation that the present moment is moving forward into the future, might be an illusion created by our perspective, by the particular way information is organized in our brains and memories. This is speculative, more speculative than the holographic principle itself, but it points to a broader pattern. As physics probes deeper into the nature of reality, many concepts that seem fundamental turn out to be emergent. Temperature, pressure, color, sound, all of these are emergent properties that arise from the collective behavior of atoms and photons. The holographic principle suggests that space and possibly time should be added to this list. They are not fundamental features of the universe, but rather useful descriptions that emerge at certain scales. Does this change anything about your experience? When you touch the wall, does it matter whether the sensation arises from a three-dimensional interaction or from information encoded on a distant boundary? The sensation is the same. The wall is equally solid. The physics that governs the interaction is identical in both descriptions. Nothing changes in terms of what you observe or measure. What changes is your understanding. You come to see that the concepts you use to describe the world, concepts like location and distance and volume, are not describing ultimate reality, but rather a particular way of organizing information, a way that works extraordinarily well for creatures like us, but that might not be the deepest possible description. And there is something liberating about this, a sense that reality is more flexible, more subtle, more interconnected than it appears. Consider quantum entanglement, the phenomenon where two particles can be correlated in ways that seem to transcend space, where measuring one particle instantly affects the state of another particle far away. Einstein called this spooky action at a distance, and it troubled him because it seemed to violate the principle that nothing can travel faster than light. But in a holographic universe, where space itself is emergent, entanglement might be more natural. If two particles are described by nearby degrees of freedom on the boundary, then they are close in the fundamental description even if they appear far apart in the emergent three-dimensional space. Their correlation is not a mysterious action across space, but a simple proximity in the underlying structure. Some physicists, notably Mark van Ramsdonk and others, have proposed that quantum entanglement is actually what creates space. In this view, space is not a pre-existing container that particles inhabit. Space is the pattern of correlations, the web of entanglement between quantum degrees of freedom. Where entanglement is strong, we perceive locations as being close together. Where entanglement is weak, locations appear far apart. Space, in this picture, is geometry built from entanglement. This idea has a precise mathematical formulation in the context of AD-CFT, and it has been explored in many papers over the past 15 years. It provides a way to think about how the geometry of the three-dimensional space emerges from the boundary theory. The shape of space, the distances between points, the curvature that we measure, all of these arise from the pattern of quantum correlations in the boundary theory. If this is correct, then when you move through space, you are not traversing a pre-existing geometry. You are navigating patterns of information, tracing paths through a network of quantum correlations that manifest to you as physical space. This does not make space less real. It makes space a different kind of thing than we thought, a thing made of information and correlation rather than a thing that simply is. Let your mind rest with this for a moment. The room around you, with its walls and its air and its furniture, might be an emergent structure, a way of organizing information that creates the experience of three-dimensional space. The atoms in your body, separated from the atoms in the wall by what seems like empty space, might be described more fundamentally as patterns on a distant boundary, patterns that are related in a way that creates the appearance and the reality of separation in the three-dimensional description. Both descriptions are true. You are here, in 3 dimensions, feeling solid matter and empty space. And simultaneously, you are a pattern of information on a boundary, a pattern that, when decoded, produces the experience of being here. There is no contradiction because the two descriptions are equivalent, two languages saying the same thing. As we move forward, we will explore what this means for consciousness, for identity, for the question of what you are in a holographic universe. But for now, let these ideas about space and time settle gently. Space might be emergent. Time might be emergent. The distances and durations we measure might be ways of organizing information rather than fundamental features of reality. And yet, nothing about your immediate experience changes. The hologram is as real as anything can be. We have established that holography is not merely a metaphor, but a precise mathematical reality, at least in certain theoretical contexts like the AD-CFT correspondence. Now we must explore this correspondence more deeply, understanding not just that it exists, but how it works and what it reveals about the fundamental nature of reality. This will require us to move slowly through ideas that are subtle and sometimes counterintuitive, but the journey is worth taking because it leads to profound insights about what the universe actually is. The AD-CFT correspondence, discovered by Juan Meldacena in 1997, connects two theories that initially appear to have nothing to do with each other. On one side, you have a theory of gravity in a space with 3 spatial dimensions plus time. This space is anti-de Sitter space, often abbreviated as ADS. It has a peculiar geometry, curved in a specific way that gives it strange properties. It is not the geometry of our actual universe, but it is a solution to Einstein's equations of general relativity, and it provides a theoretical laboratory where physicists can explore quantum gravity. On the other side of the correspondence, you have a conformal field theory, abbreviated CFT, which is a quantum theory of particles and fields living on the boundary of the AD space. This boundary has one fewer spatial dimension. If the interior is 3-dimensional space plus time, the boundary is 2-dimensional space plus time. Importantly, this boundary theory has no gravity. It is a quantum field theory, similar to the theories that describe electromagnetic forces or the strong nuclear force, but it does not include general relativity. There is no space-time curvature, no black holes, no gravitational dynamics in the boundary theory itself. What Meldacena proved is that these two theories are exactly equivalent. Every possible state in the gravitational theory corresponds to a state in the boundary theory. Every process, every measurement, every calculation you can do in one theory has a translation in the other theory that gives precisely the same result. They are not approximations of each other. They are exact dual descriptions, like 2 different languages that express precisely the same information. This equivalence is often called a duality. Physicists use the word duality to describe situations where 2 apparently different theories are actually the same theory in disguise. But this is not an ordinary duality. This is a duality between theories with different numbers of dimensions, between a theory with gravity and a theory without gravity, between descriptions that seem fundamentally incompatible. Let us explore what this means through a specific example. Suppose you want to understand a black hole in the AD space. You can describe this black hole using general relativity. You can calculate its event horizon, its temperature, its entropy, how it responds to perturbations, how it emits Hawking radiation. All of these are standard calculations in gravitational physics, using the equations of general relativity and quantum field theory in curved spacetime. But according to the AD-CFT correspondence, you can also describe this exact same black hole using the boundary theory. In the boundary theory, there is no black hole object. There is no event horizon. There are only quantum fields on the 2-dimensional boundary, interacting with each other according to the rules of quantum mechanics. Yet when you calculate the properties of these quantum fields in a particular highly excited state, you find that the results match exactly the properties of the black hole in the interior. The black hole's temperature corresponds to a temperature in the boundary theory. The black hole's entropy corresponds to the entropy of the boundary state. When the black hole emits Hawking radiation, This corresponds to thermal emission from the boundary state. The black hole is not separate from the boundary theory. The black hole is a way of describing a particular configuration of the boundary theory. This is astonishing. A black hole, one of the most dramatic objects in gravitational physics, an object whose very existence depends on the curvature of space-time, can be completely described by a theory that has no gravity and one fewer dimension. The three-dimensional interior, including the black hole and all the space around it, emerges from the two-dimensional boundary. The geometry itself is not fundamental. It is derived, emergent, holographic. How can geometry emerge from a theory that has no geometry to begin with? The answer lies in quantum entanglement, the strange correlations between quantum systems that Einstein found so troubling. In the boundary theory, different regions of the boundary are entangled with each other. The pattern of this entanglement, the strength of the correlations between different parts of the boundary, encodes information about the geometry of the interior space. When the entanglement is strong and organized in particular ways, the interior geometry is smooth, well-defined, describable by ordinary general relativity. When the entanglement is weak or disorganized, the interior geometry becomes fuzzy, quantum, perhaps not well-defined at all. The distance between 2 points in the interior corresponds to the amount of entanglement between the corresponding regions on the boundary. The curvature of space in the interior corresponds to patterns in how the entanglement is distributed. This idea, that geometry arises from entanglement, has been explored in great detail by physicists like Mark van Ramsdonk, Brian Swingle, and many others. It provides a concrete mechanism for how space emerges in holographic theories. Space is not put in by hand. It is a derived concept, a way of organizing information about quantum correlations. Think about what this means. When you measure the distance between two objects, when you use a ruler or send a light beam and measure the travel time, you are actually probing the entanglement structure of the underlying quantum state. Distance is not a fundamental property. It is an emergent property that arises from how information is correlated. This has profound implications for quantum gravity. One of the great challenges in theoretical physics is to combine quantum mechanics and general relativity into a single coherent framework. These two theories are our most successful descriptions of nature, but they seem incompatible at a deep level. Quantum mechanics describes the world in terms of wave functions and probabilities. General relativity describes the world in terms of curved space-time geometry. Attempts to merge them directly lead to mathematical inconsistencies and infinities that cannot be easily resolved. But the holographic principle offers a different approach. Perhaps the way to understand quantum gravity is not to try to quantize space-time directly, but rather to describe physics using a theory that does not have gravity or space-time to begin with, and then derive gravity and space-time as emergent phenomena. The boundary theory in AD-CFT is precisely such a theory. It is a quantum theory without gravity, and yet it contains all the information needed to describe a gravitational theory in a higher dimensional space. This suggests that the problems of quantum gravity might be solved not by finding the right way to make space-time quantum, but by recognizing that space-time is not fundamental. At the deepest level, the universe might be described by a quantum theory that has no space and no time in its fundamental formulation. Space and time emerge from this theory in a particular limit, in the same way that fluid mechanics emerges from the statistical behavior of molecules. If this is correct, then questions about what happens at the center of a black hole, or what occurred at the very beginning of the universe during the Big Bang, might not have answers in terms of space-time geometry, because space-time itself breaks down or becomes ill-defined in those extreme situations. Instead, these questions would need to be rephrased in terms of the more fundamental, non-spatial theory. Let us pause and take a breath. These ideas are dense and challenging, The notion that space itself emerges from entanglement, that geometry is derived rather than fundamental, that a three-dimensional gravitational universe is exactly equivalent to a two-dimensional non-gravitational theory. All of this pushes hard against our intuitions about what is real and what is fundamental. But this is where the mathematics leads. The AD-CFT correspondence is not a vague philosophical idea. It is a precise mathematical statement that has been tested in thousands of calculations over the past 25 years. Every test has confirmed the equivalence. The correspondence works. It is real, and it tells us something profound about the nature of reality. As your mind absorbs these ideas, you might notice a curious effect. The more you think about space as emergent, the less solid and fixed it seems. The room around you begins to feel less like a container and more like a description, a way of organizing information. This is not a loss of reality. If anything, it is a deepening of reality, a recognition that what we call real is richer and stranger than the simple picture of objects in space. Let yourself rest in this strangeness for a moment. You do not need to understand every detail. The key point is this. The holographic principle is not speculation. It is mathematics, and it reveals that the universe can be described in radically different ways, with different numbers of dimensions, with and without gravity, and these different descriptions are exactly equivalent. Reality is not one thing. It is a relationship between descriptions, and we are only beginning to understand what that means. Now we must confront a question that naturally arises. If the holographic principle is real, and if it applies to black holes in theoretical spaces like ADS, does it apply to our actual universe? Are we living in a hologram? Is the reality we experience every day a projection from a distant boundary? The honest answer is that we do not know for certain. Our universe is not an AD space. The geometry of our universe is different. Space is expanding, accelerating in its expansion due to dark energy, and this gives our universe a different structure than the negatively curved, static AD space, where the holographic correspondence has been proven rigorously. However, many physicists believe that the holographic principle is more general than the specific AD-CFT correspondence. The principle might apply to any region of space, including regions in our universe. The reason for this belief comes from the connection between holography and entropy, specifically the way that entropy in gravitational systems seems to be proportional to surface area rather than volume. We discussed earlier how black hole entropy is proportional to the area of the event horizon. This is not just true for black holes in AD space. It is true for black holes in our universe as well. Any black hole, regardless of what kind of space it sits in, has an entropy given by the Bekenstein-Hawking formula, proportional to the area of its horizon. This universality suggests that holography is a general feature of gravity, not just a peculiarity of AD space. Furthermore, our universe has a horizon of its own, a boundary that divides what we can observe from what we cannot. This is the cosmological horizon, and it arises from the expansion of space. Because space is expanding, and because that expansion is accelerating, there is a maximum distance from which light can reach us. Beyond the cosmological horizon, space is receding from us faster than light can traverse the growing distance. So signals from those distant regions can never arrive, no matter how long we wait. This cosmological horizon is not just a limitation on our ability to observe. It is a real feature of space-time, a surface beyond which events are causally disconnected from us. And interestingly, this horizon has an entropy. Just as a black hole has entropy proportional to the area of its event horizon, the cosmological horizon appears to have an entropy proportional to its area. This suggests that the cosmological horizon might function as a holographic boundary for our observable universe. All the information about everything we can observe, all the particles, all the fields, All the events in cosmic history might be encoded on this distant surface. The three-dimensional space we inhabit, with its galaxies and stars and planets, might be a holographic projection from this two-dimensional boundary. If this is true, it has strange implications. The boundary is moving away from us as space expands. Currently, it is roughly 16 billion light-years away in proper distance, though that distance is increasing over time. Everything you see, everything you experience, everything that happens in the observable universe corresponds to information encoded on this receding surface. But we must be careful not to take this picture too literally. The cosmological horizon is not a physical wall. You could travel toward it, and as you move, it would move away from you, always staying at the same proper distance in your reference frame. It is not a place you can reach or touch. It is a boundary in space-time, a dividing line between regions that can communicate and regions that cannot. Moreover, the idea that information is encoded on this horizon is not yet as rigorously established as the AD-CFT correspondence. It is an extrapolation, a proposal based on the successes of holography in other contexts, but not yet proven mathematically in the same way. Some physicists are working on making this idea precise, developing what is sometimes called de Sitter holography or cosmological holography, where de Sitter space is a model for the expanding universe with dark energy. These efforts are ongoing, and the picture is not yet complete, but the clues are suggestive. Entropy bounds, the success of AD-CFT, the properties of black holes, all of these point toward a holographic structure for our universe, even if we do not yet have the full mathematical framework to describe it. What would it mean, practically, if our universe is holographic? Would anything change in our daily lives or in our scientific observations? The answer is mostly no, at least not directly. The holographic description and the standard three-dimensional description are equivalent, giving the same predictions for all measurements we can make. The physics we know, the laws that govern chemistry and biology and engineering, would remain exactly the same. But there might be subtle effects at extreme scales. If space is fundamentally pixelated at the Planck scale, if there is a finite amount of information per unit area, then there could be tiny deviations from perfect smoothness in the fabric of spacetime. These deviations might show up in very precise measurements of the cosmic microwave background radiation, the ancient light from the early universe, or in the behavior of gravitational waves, or in other phenomena that probe the structure of spacetime at the smallest scales. Some experiments have been proposed to look for evidence of holography. One example is the holometer experiment at Fermilab, which used extremely sensitive interferometers to search for holographic noise, tiny random fluctuations in the positions of objects that would arise if spacetime has a discrete structure at the Planck scale. The experiment ran for several years and did not detect the predicted signal, but this null result helps to constrain the possible forms that holographic noise could take. Another source of hints comes from studies of quantum entanglement in condensed matter systems and in quantum field theories that can be simulated on computers. Physicists have found that in many different systems, the entanglement entropy of a region is proportional to the area of its boundary, not its volume. This area law for entanglement seems to be a general feature of quantum theories, appearing in systems ranging from models of magnetism to theories of elementary particles. The prevalence of area laws in entanglement entropy suggests that holography might be a very general principle, emerging in many contexts beyond just quantum gravity. It might reflect something deep about how information is organized in quantum systems, a principle that applies universally and that happens to manifest as holography when you consider theories with gravity. Let your thoughts drift through these possibilities. The universe you inhabit might be a hologram, a projection from a distant boundary where all information is encoded in two dimensions. Or perhaps holography applies in some other way, perhaps more locally, with every region's information encoded on its surrounding surface. Or perhaps our universe is not holographic in exactly the way ad space is, but follows some related principle that we have not yet discovered. The uncertainty here is not a weakness. It is a reflection of where we are in the scientific process, at the frontier where knowledge is being actively created. We know that holography is real in certain contexts. We have strong reasons to believe it applies more broadly. But the exact way it applies to our universe remains an open question, a puzzle that physicists are working to solve. What we can say with confidence is this: the holographic principle has fundamentally changed how physicists think about space, time, and information. It has revealed that reality can be described in multiple equivalent ways, that dimensions can be emergent rather than fundamental, that gravity itself might be a derived phenomenon arising from more basic quantum structures. These insights will shape physics for decades to come, regardless of whether our specific universe turns out to be holographic in precisely the way some theories suggest. And there is something deeply satisfying about this uncertainty, this sense of being at the edge of understanding. Science is not a collection of final answers. It is a process of asking questions, testing ideas, and revising our understanding based on evidence. The holographic principle is part of this process, a profound idea that emerged from the mathematics of theoretical physics, and that continues to evolve as we learn more. As we continue this journey, exploring what holography means for consciousness and identity and the nature of existence itself, carry with you this sense of being at the frontier. The solid ground of absolute certainty is behind us. We are in territory where possibilities multiply, where the nature of reality itself is up for discussion, where the answers are not yet known. And there is a strange freedom in this, a release from the need to have everything figured out, an acceptance of mystery as part of the structure of the universe. If we accept, at least as a possibility, that our universe might be holographic, that the three-dimensional reality we experience emerges from information encoded on a two-dimensional boundary, then we must ask, what does this mean for us? What are we in a holographic universe? Where is consciousness located? Where does identity reside? These questions touch on the deepest mysteries of existence, the relationship between physical processes and subjective experience, the nature of the self. Holography does not solve these mysteries, but it reframes them in interesting ways, suggesting new perspectives on old questions. Let us start with a simple question. Where are you? In everyday terms, the answer is obvious. You are here, in this room, occupying a particular location in three-dimensional space. Your body is a collection of atoms organized in a specific structure, held together by electromagnetic and chemical forces, occupying a volume of space roughly 2 meters tall and half a meter wide. You are a physical object with a location, a place, a here. But in a holographic universe, this description is not the only valid one, and perhaps not the most fundamental one. According to the holographic principle, all the information that defines you, every atom in your body, every chemical reaction, every neural firing in your brain, is also encoded on the boundary of the observable universe, on that distant cosmological horizon 16 billion light-years away. The pattern of information on that boundary includes a complete description of you, and when that pattern is decoded, when the holographic projection is performed, the result is you here in 3 dimensions. So where are you really? Are you here in this room, or are you on the boundary? The holographic principle says this question has no unique answer. Both descriptions are equally valid. Both are complete. The you that exists here is not a copy of information on the boundary. You are the information on the boundary, viewed from a particular perspective, decoded into 3 dimensions. This might sound like semantics, but it has interesting implications. If you are fundamentally a pattern of information, and if that information is encoded on a boundary, then your location in three-dimensional space is not as fundamental as it seems. The space around you, the distances between your body and other objects, these are emergent properties of how the information is organized. In the boundary description, you do not occupy a location in the same way. You are a pattern in a two-dimensional field, and location in the three-dimensional sense is a derived concept that emerges from relationships within that pattern. What about consciousness? Consciousness is perhaps the most mysterious phenomenon in the universe. The fact that there is something it is like to be you, that you have subjective experiences, that the world appears to you from a particular perspective. The relationship between consciousness and physical processes is not understood. We know that consciousness is associated with brain activity, that damaging certain parts of the brain affects consciousness in specific ways, that anesthetics can turn consciousness off and then back on. But we do not know how physical processes give rise to subjective experience, how matter becomes aware. Holography does not solve this problem, but it offers an interesting perspective. If consciousness arises from information processing in the brain, from patterns of neural activity that integrate information and generate responses, then consciousness is associated with a particular organization of information. In the three-dimensional description, this information is encoded in the connections between neurons, in the firing patterns of neural networks, in the chemical gradients across synapses. In the boundary description, the same information is encoded in patterns on the two-dimensional surface. The question of where consciousness resides might not have a meaningful answer. Consciousness is associated with a pattern of information, and this pattern has multiple equivalent descriptions. In one description, consciousness is here in your brain, arising from three-dimensional neural activity. In another description, consciousness is on the boundary, arising from patterns in a two-dimensional field. These are not two separate consciousnesses. They are one consciousness described in two ways. This might seem like it dissolves the reality of consciousness, reducing it to mere information processing. But actually, it might point towards something deeper. If consciousness is fundamentally about information and its organization, and if information is preserved across different descriptions, then consciousness is more fundamental than any particular physical substrate. Your consciousness does not depend on being made of atoms in three-dimensional space. It depends on the pattern, on the relationships, on the information structure. And that structure exists whether you describe it in 3 dimensions or 2 dimensions, or perhaps in other ways we have not yet imagined. There is something liberating about this perspective. You are not trapped in a particular location or a particular physical form. You are a pattern of information that can be described in multiple ways. The boundary description and the interior description both capture what you are, completely and exactly. Neither is more real than the other. What about personal identity over time? You change constantly. Atoms in your body are replaced. Neural connections strengthen and weaken. Memories form and fade. Yet you maintain a sense of being the same person, a continuity of identity from moment to moment and year to year. In a holographic universe, this continuity is a continuity of pattern, of information structure that persists even as the details change. In the boundary description, your identity over time is a pattern in the 2-dimensional field that evolves according to the laws of quantum field theory. In the interior description, your identity is a pattern in 3-dimensional space that evolves according to the laws of biology and chemistry and neuroscience. These are 2 descriptions of the same continuity, 2 ways of expressing the persistence of a particular information structure through time. The holographic principle suggests that identity is not about being made of particular atoms or occupying a particular location. Identity is about pattern, about information, about relationships. And patterns can be described in many ways. You are the pattern, not any specific description of the pattern. Some people find this troubling, as if it diminishes the reality of the self. If I am just information, they ask, does that mean I am not real? Does it mean I do not matter? But this conclusion does not follow. Information is real. Patterns are real. The relationships that define you are as real as anything in the universe. The holographic principle does not make you less real. It reveals that what you are is more subtle, more flexible, more fundamental than you might have thought. Consider an analogy. A novel exists as patterns of ink on paper, as magnetic states in a computer's memory, as electrical signals flowing through the internet, as sound waves when read aloud. The novel is none of these substrates specifically. The novel is the information, the pattern of words and meanings that persists across all these different physical implementations. And the novel is real. The story is real. The meanings are real, even though they transcend any particular physical form. Similarly, you are real, not because you are made of particular atoms in a particular place, but because you are a pattern that persists, that maintains its structure, that processes information and responds to the world in characteristic ways. The holographic principle tells us that this pattern can be described in multiple equivalent ways, but the pattern itself, the information structure that is you, is fundamental and real. Let these ideas settle slowly. The question of what you are in a holographic universe does not have a simple answer, but it points toward a view of identity that is based on information and pattern rather than on substance and location. You are not your atoms. You are not your location in space. You are the relationships, the correlations, the information structure that those atoms and that location represent. And that structure is real, whether described in 3 dimensions or 2, whether located here or encoded on a distant boundary. There is a deep peace in this understanding. If you are fundamentally information, fundamentally pattern, then you are not as fragile as you might fear. Atoms can be replaced. Locations can change. Physical forms can transform. But the pattern persists. The information endures. And as long as the pattern exists, you exist in whichever description we choose to use. Now we can explore how this holographic view affects our understanding of connection and separation, of the boundaries between self and other, of the nature of the space that seems to divide us. In ordinary experience, you and I are separate. You are there, I am here, and space divides us. We are distinct individuals, separated by distance, existing independently. But in a holographic universe, this separation is less fundamental than it appears. If all the information about both of us is encoded on the same boundary, if the space between us is emergent rather than fundamental, then the division between us is a feature of one particular description, not a fundamental truth about reality. In the boundary description, you and I are patterns in the same 2-dimensional field. We are not separated by space because space does not exist yet in the boundary description. We are simply different aspects of the same quantum state, different regions of the same field, related by quantum entanglement and interactions. The distinction between us arises when we translate to the 3-dimensional description, when we decode the hologram and see separate objects in separate locations. This does not mean we are literally the same entity. The patterns that define you and me are different. We have different information content, different structures. But the separation, the sense of being isolated individuals occupying different regions of space, is an emergent property of the 3-dimensional description. At the boundary level, we are parts of a unified whole, regions of a single quantum field. Quantum entanglement makes this even more interesting. When 2 particles are entangled, measuring one affects the other instantly, regardless of the distance between them. This puzzled Einstein, who called it spooky action at a distance. But in a holographic universe, entanglement might be the fundamental connection, and distance might be the derived concept. If two entangled particles correspond to nearby regions on the boundary, then they are close in the fundamental description even if they appear far apart in 3 dimensions. The correlation between them is not action across space, but rather proximity in the boundary field. Space is not dividing them. Space is emergent, arising from the pattern of entanglement, and strongly entangled particles create a short distance in the emergent space. Some physicists have taken this idea very seriously, proposing that entanglement is what creates space, that the geometry of space-time is built from the web of quantum correlations. This is sometimes expressed in the slogan, "Entanglement builds geometry." Where entanglement is strong, space is well-defined and distances are short. Where entanglement is weak, space becomes fuzzy and distances grow large. If this is correct, then when you look at another person across a room, the space between you is not empty vacuum. It is a manifestation of entanglement patterns, a geometric representation of quantum correlations. The distance you measure is emergent from these correlations. At the boundary level, you and that other person are regions of the same field, and the relationship between you is more direct, more immediate than the 3-dimensional picture suggests. This has implications for how we think about consciousness and communication. When two people communicate, when you speak and I listen, information flows from you to me. In the 3-dimensional description, this information travels as sound waves through air, as vibrations in molecules, crossing the space between us. In the boundary description, the same information transfer occurs, but without crossing space because space is emergent. The information flows through correlations in the quantum field, a change in your pattern affecting a change in my pattern through the fundamental connections that underlie space-time itself. Again, this does not make communication less real. The holographic description and the 3-dimensional description are equivalent. Information still flows. Messages are still sent and received. But the underlying mechanism is more direct, more unified than it appears. At the deepest level, we are connected through the structure of the quantum field on the boundary, and the space that seems to divide us is a way of organizing and describing these connections. There is something profound here about the nature of isolation and connection. In everyday life, we feel separate, isolated by the space around us, alone in our own consciousnesses. But if reality is holographic, if space is emergent from entanglement, then this isolation is not fundamental. We are separate in the sense that we are different patterns, different information structures. But we are connected through the quantum field that describes us both, through the entanglement that creates the space between us, through the unified whole of which we are both aspects. This might sound mystical, but it is grounded in mathematics. The AD-CFT correspondence shows explicitly that objects in the interior space, objects that appear separate and distant from each other, correspond to regions of the boundary field that are related by quantum correlations. The interior separation emerges from the boundary relationships. The fundamental description is unified. The emergent description is divided into separate objects in separate locations. Spiritual traditions have long spoken of underlying unity, of the illusion of separation, of all beings as manifestations of a single reality. The holographic principle does not prove these ideas, but it offers a scientific framework where similar concepts emerge naturally. The unity is the quantum field on the boundary. The separation is the 3-dimensional description we inhabit. Both are real, both are valid, but one is more fundamental, and recognizing this might change how we relate to each other and to the universe. As you rest in these thoughts, consider how it feels to think of yourself not as an isolated object in space, but as a pattern in a unified field, connected through quantum correlations to everything else, separated by emergent space, but unified at a deeper level. This is not a loss of individuality. Your pattern is unique, Your information structure is yours alone. But the loneliness of separation, the sense of being utterly isolated in your own consciousness, might soften when you recognize that the space creating that isolation is not fundamental, that you and everything else are aspects of the same underlying reality, described in different ways. Let this understanding bring comfort. You are not alone. You are part of a unified whole. The boundaries that seem absolute are flexible, emergent, ways of organizing information rather than ultimate truths. And in a holographic universe, connection is more fundamental than separation, unity more basic than isolation, relationships deeper than the space that seems to divide us. We have explored the theoretical foundations of holography, the mathematical proof through AD-CFT, and the implications for space, time, consciousness, and identity. Now we must ask, is there evidence? Can we test whether our universe is actually holographic? And if so, what experiments have been done, what results have been found, and what might we discover in the future? The honest answer is that we do not yet have definitive proof that our universe is holographic. The AD-CFT correspondence is proven mathematically, but it applies to a theoretical space that is not quite like our universe. The extension of holographic principles to our actual cosmos remains an active area of research, with proposals and conjectures, but not yet the kind of rigorous proof that exists for AD-CFT. However, there are clues, hints in the data, and experiments designed to search for signatures of holography. Let us explore these carefully, understanding both what has been observed and what remains uncertain. One of the earliest hints came from an unexpected place. In 2008, scientists at the GEO 600 gravitational wave detector in Germany were puzzled by a persistent noise in their instrument, a mysterious signal that could not be explained by any known source. The detector was designed to measure tiny ripples in space-time caused by colliding black holes or neutron stars, but instead of clean data, they were seeing a fuzzy background noise that limited their sensitivity. Craig Hogan, a physicist at Fermilab, proposed an intriguing explanation. He suggested that this noise might be holographic noise, a fundamental graininess in space-time itself arising from its holographic structure. If space is pixelated at the Planck scale, if there is a fundamental limit to how precisely positions can be defined, then there would be tiny random fluctuations in the apparent positions of objects, like static on a television screen. These fluctuations would show up as noise in extremely sensitive instruments like gravitational wave detectors. Hogan calculated what this holographic noise should look like and found that its properties roughly matched the mysterious signal at GEO 600. The frequency spectrum, the amplitude, several features seemed consistent with what you would expect if space-time has a discrete structure at very small scales. This was exciting but far from conclusive. There were other possible explanations for the noise, technical issues with the instrument, environmental disturbances, known sources that had not been fully accounted for. To test the idea more rigorously, Hogan and his collaborators built a dedicated instrument called the holometer at Fermilab. This was a specialized interferometer designed specifically to search for holographic noise, with careful shielding against conventional noise sources and configurations optimized to detect the predicted signal. The holometer ran for several years, collecting data with unprecedented sensitivity to the kinds of fluctuations that holographic spacetime would produce. The results, published in 2016, were negative. The holometer did not detect holographic noise at the level Hogan had predicted. This does not disprove holography, but it rules out certain simple models of how holographic pixelation might manifest. Perhaps the noise is smaller than predicted, or perhaps it has a different character that the experiment was not sensitive to, or perhaps the holographic structure of space-time does not produce this kind of noise at all. The null result from the holometer is actually valuable. It constrains possibilities. It tells us that if space-time is holographic, the holography must be subtle, not producing large random fluctuations in positions. This is consistent with the idea that holography is an exact equivalence, where the boundary description and interior description give precisely the same predictions. If they are truly equivalent, there should be no observable difference, no noise or graininess that distinguishes one description from the other. Other searches for holographic effects have looked at the cosmic microwave background, the ancient light from the early universe that fills the sky with faint microwave radiation. The CMB carries information about the state of the universe when it was only 380,000 years old, a snapshot of the cosmos in its infancy. Any features of space-time structure, including holographic properties, might leave subtle imprints in this radiation. Researchers have analyzed the CMB with extraordinary precision, measuring tiny variations in temperature across the sky, looking for patterns that might reveal holographic structure. So far, the CMB appears consistent with standard cosmology, with no clear signature of holography. But the search continues, and future experiments with even greater sensitivity might detect effects that current instruments cannot resolve. There is also theoretical work exploring how holography might be tested through quantum entanglement experiments. If entanglement is what creates space, if the geometry of space-time emerges from patterns of quantum correlations, then carefully designed experiments that measure entanglement in quantum systems might reveal this connection. Physicists are working on proposals for such experiments, using quantum computers and advanced quantum technologies to probe the relationship between entanglement and geometry. One approach involves creating quantum states with specific entanglement patterns and seeing if they produce emergent spatial structure in ways predicted by holographic theories. Another involves looking for violations of locality, situations where particles that appear far apart in space influence each other in ways that only make sense if space is emergent and they are actually close in the boundary description. These experiments are challenging, requiring exquisite control over quantum systems, but they might provide direct evidence for holographic principles. Let us take a moment to absorb what this means. We are at the frontier of human knowledge, at the boundary between what we know and what we are trying to discover. The holographic principle is not proven for our universe, but it is a serious scientific hypothesis, motivated by deep theoretical considerations and being actively tested through experiments. The absence of definitive evidence so far does not mean the principle is wrong. It might mean we have not yet looked in the right place or with sufficient precision. Science progresses through this process of proposal, prediction, and testing. Ideas emerge from mathematics, make predictions about what we should observe, and then experiments either confirm those predictions or force us to revise the ideas. The holographic principle is in the middle of this process, a beautiful theoretical structure that makes sense mathematically and might describe our universe, but that still needs empirical validation. There is a particular kind of satisfaction in being uncertain and not knowing the answer yet. It means the universe still has secrets to reveal. It means our understanding is incomplete, evolving, growing. And it means that future observations might change everything, might reveal that reality is even stranger than we currently imagine. As you let these thoughts settle, consider how it feels to live in a time when such profound questions are being actively investigated. Previous generations could only wonder about the nature of reality. We can calculate, propose experiments, collect data, and gradually narrow the space of possibilities. We might not have final answers, but we have a process for approaching them, and that process is unfolding in real time. The holographic principle is sometimes confused with another idea about reality, the simulation hypothesis. Both suggest that the reality we experience might not be fundamental, that there might be a deeper level of description. But these are very different ideas, and it is important to distinguish them carefully. The simulation hypothesis, popularized by philosopher Nick Bostrom, argues that if civilizations can develop the technology to run detailed simulations of conscious beings, and if they choose to run many such simulations, then statistically, we are more likely to be in a simulation than in the base reality. It is an argument from probability and technology, suggesting that simulated universes might vastly outnumber real universes simply because advanced civilizations could create many simulations. The holographic principle is not about simulation. It is about the mathematical structure of physics. It says that the information content of our universe can be described using a theory with fewer dimensions, that three-dimensional space emerges from two-dimensional information. But both descriptions are physical, both are governed by the laws of physics, and neither is more real than the other. In a simulation, there would be a base reality where computers run, where programmers write code, where the fundamental laws are potentially different from the laws in the simulation. The simulated universe would be derivative, dependent on the base reality, potentially capable of being turned off or modified by external agents. In a holographic universe, there is no external reality, no programmer, no computer outside the system. The boundary theory and the interior theory are two equally valid descriptions of the same physical reality. There is no one watching from outside, no one who could modify the laws or turn off the universe. The holographic equivalence is internal to physics itself, a relationship between different mathematical descriptions of the same physical situation. That said, there is an interesting parallel. Both ideas challenge the notion that the three-dimensional space we perceive is the fundamental arena of reality. The simulation hypothesis says that three-dimensional space might be computed, arising from processes in a more fundamental reality. The holographic principle says that three-dimensional space emerges from information in two dimensions. Both involve a kind of projection or encoding, but the differences are more important than the similarities. The simulation hypothesis is ultimately metaphysical, resting on assumptions about what advanced civilizations might do and on probabilistic reasoning that is difficult to test empirically. The holographic principle is physics, arising from the mathematics of quantum field theory and general relativity, making specific predictions that can in principle be tested through experiments. Some people find the simulation hypothesis troubling because it suggests we might not be real, that our experiences might be artificial, that nothing truly matters if we are just code running in a computer. The holographic principle does not have these implications. It says that reality can be described in multiple equivalent ways, but all descriptions are real, all are physical, all matter equally. You are not less real for being describable holographically. The information pattern that defines you exists, whether we describe it using 3 dimensions or 2 dimensions. The experiences you have are genuine physical processes, whether we analyze them in the interior theory or the boundary theory. The holographic principle changes our understanding of what reality is, but it does not diminish the reality of experience. Let yourself feel the distinction. The simulation hypothesis invites a kind of ontological vertigo, a worry that everything might be fake, that you might be a temporary construct in someone else's computer. The holographic principle invites wonder at the flexibility of reality, at the fact that the universe can be described in multiple ways, but it offers no reason to doubt the reality of your experience. You are as real as anything in the universe, whether that universe is 3-dimensional or holographic. If anything, the holographic principle is reassuring in a way the simulation hypothesis is not. It says that information is fundamental, that patterns persist, that the structure of reality is mathematical and eternal. You are a pattern in this structure, and patterns do not disappear. They transform, evolve, relate to other patterns, but the information itself is conserved. In a holographic universe, nothing is ever truly lost. Now we must ask, if we accept, provisionally, that we might be living in a holographic universe, how should we live? Does this knowledge change anything about how we conduct our daily lives, how we relate to each other, how we find meaning and purpose? The practical answer is, not much changes. The physics of everyday life is the same whether we describe it three-dimensionally or holographically. Water still boils at 100 degrees Celsius. Gravity still pulls objects downward. Light still travels at 300 million meters per second. The chemical reactions in your body still proceed according to the same rules. The holographic description and the standard description make identical predictions for all these phenomena. But something changes in understanding, in perspective, in how we think about what we are and what the world is. And this change in understanding might have subtle effects on how we live, even if it does not change the physical laws we must navigate. First, there is the perspective on space and separation. If space is emergent, if the distances between us arise from entanglement patterns rather than being fundamental, then the isolation we feel might be less absolute than it appears. We are separated in the three-dimensional description, yes, each of us occupying a distinct location, unable to directly access each other's thoughts or experiences. But in the boundary description, we are regions of the same field, connected by quantum correlations, aspects of a unified whole. This does not give us telepathy or allow us to violate causality, but it might change how we think about our relationship to others and to the universe. The space that divides us is real in the three-dimensional description, but it is derived, emergent, a way of organizing information. At a deeper level, we are more connected than the spatial picture suggests. There is also the perspective on change and impermanence. In everyday life, we are acutely aware that everything changes, that nothing lasts, that all structures eventually decay. This is true whether the universe is holographic or not. But the holographic principle offers a different way of thinking about what persists and what changes. If you are fundamentally a pattern of information, and if information is conserved, then even as the physical substrate changes, even as atoms are replaced and locations shift, the pattern persists. The holographic description might be more stable, more fundamental than the three-dimensional description where things seem constantly in flux. Your identity, your memories, your relationships, all of these are information structures that persist in the boundary theory even as their three-dimensional representations change. This is not immortality in any conventional sense. Patterns can dissolve, information can be scrambled, structures can lose coherence. But it suggests that what we are is less fragile than it seems when we think of ourselves as collections of atoms in specific locations. We are information, and information has a different kind of persistence than matter. There is also a perspective on free will and determinism. In both the boundary theory and the interior theory, the laws of physics are deterministic at the fundamental level, though quantum mechanics introduces intrinsic randomness. Whether you have free will in any meaningful sense is a question that philosophy and neuroscience struggle with, and holography does not resolve it. But it offers an interesting angle. If consciousness arises from information processing, from patterns that integrate information and generate responses, then consciousness exists in both descriptions equally. In the boundary theory, your decisions are part of the evolution of the quantum field according to its dynamical laws. In the interior theory, your decisions are part of the evolution of your brain state according to the laws of neuroscience. These are equivalent descriptions of the same process. The question of whether this process constitutes free will is independent of holography, but recognizing that you can be described in multiple equivalent ways, that there is no single level of description that is uniquely real, might offer a kind of freedom. You are not just a mechanical object following deterministic laws in three-dimensional space. You are also a pattern in a quantum field, a structure of information that processes and responds and creates. Both descriptions are true, and neither is complete without the other. How we live in a holographic universe might not be about changing specific behaviors, but about carrying a different sense of what we are. We are information patterns in a universe that can be described mathematically in multiple equivalent ways. We are both isolated objects in three-dimensional space and connected aspects of a unified field. We are both temporary physical structures and persistent patterns of information. This multiplicity of description can be empowering. When you feel trapped by circumstances, limited by physical constraints, remember that there are other descriptions, other ways of understanding what is happening. The boundary theory and the interior theory are both real, both complete. Neither has priority, and this means that reality is richer, more flexible, more mysterious than any single description can capture. Let yourself rest in this multiplicity. You are a three-dimensional being, yes, feeling weight and warmth and the pressure of the floor beneath you. And you are also a pattern on a distant boundary, a configuration of a quantum field that happens to create the experience of being here. Both are true. Both are you. And in this dual nature, there is a strange freedom, a recognition that what you are cannot be reduced to any single description, that you exist in the relationship between descriptions, in the mathematical structure that connects them. We are nearing the end of this exploration, this journey through the holographic principle and its implications for reality. As we prepare to rest, to let these ideas fade into the background as sleep approaches, let us consider what the holographic universe means at the largest scale, the cosmic scale, where space and time themselves become questions rather than answers. The boundary of the observable universe, the cosmological horizon, is receding from us as space expands. It is currently about 16 billion light years away in proper distance. But this distance grows every moment as the expansion of space accelerates. Everything we can ever observe, every galaxy, every star, every photon of light that has reached us or ever will reach us, comes from inside this boundary. Beyond it lies a vast cosmos that we cannot access, regions of space that are causally disconnected from us, forever beyond our ability to observe or influence. If our universe is holographic, then all the information about everything inside this boundary is encoded on the boundary itself. The cosmological horizon is not just a limitation on our observations. It is a two-dimensional surface on which the complete description of the observable universe is written. Every event in cosmic history, every particle, every quantum state, corresponds to information on this surface. As the universe ages, as space continues to expand and the horizon recedes, galaxies that are currently visible will eventually cross beyond the horizon. Their light will become more and more redshifted, stretched to longer and longer wavelengths by the expansion of space, until finally it fades beyond detection. These galaxies will not be destroyed. They will simply slip beyond the boundary of what we can observe, moving into the vast, unobservable cosmos beyond the horizon. In the holographic description, this means that information about those galaxies will cease to be part of our boundary. The holographic screen will no longer encode them. From our perspective, they will have left the universe, not by traveling to another place, but by crossing the boundary that defines what is observable and what is not. This has implications for the ultimate fate of the universe. As expansion continues, the observable universe will gradually contain fewer and fewer galaxies. The ones that remain will be those gravitationally bound to our local cluster, the galaxies near enough that gravity overcomes cosmic expansion and holds them together. Everything else will recede beyond the horizon, fading from view, removed from our holographic description. In the far future, trillions of years from now, observers in our galaxy or its descendants will look out and see almost nothing. The cosmic microwave background will have redshifted to wavelengths so long that it becomes undetectable. Distant galaxies will have vanished beyond the horizon. The observable universe will consist of the local group and nothing else, an island of matter in an otherwise empty and expanding space. Eventually, even the galaxies in the local group will disperse. Stars will die, black holes will evaporate, matter will decay if protons are unstable, as some theories suggest. The universe will approach a state of maximum entropy, a condition where all gradients have been smoothed out, all usable energy has been expended, and nothing changes because there is no energy available to drive change. This is sometimes called the heat death of the universe, a term that sounds grim but actually describes a state of perfect equilibrium. The universe will not end in fire or violence. It will cool and dim and settle into stillness, a vast dark expanse at a temperature infinitesimally above absolute zero, where nothing interesting happens because everything has reached the same energy state. In this far future, what happens to the holographic boundary? If the universe has reached maximum entropy, if all information has been maximally dispersed, then the entropy of the universe equals the maximum possible given by the area of the cosmological horizon. The holographic screen is saturated with information, but that information is completely randomized, encoding a state of total disorder. From the three-dimensional perspective, the universe is empty and cold. From the boundary perspective, the quantum field is in a thermal state, a high-entropy configuration where all patterns have dissolved into noise. Both descriptions capture the same reality, a universe that has expended all its capacity for change, that has reached its final resting state. There is something both melancholic and peaceful about this vision. All the complexity of the current universe, all the stars and galaxies, all the life and consciousness that has emerged, will eventually fade into this uniform state. The patterns will dissolve, the structures will decay, the information will persist, but in a form so scrambled that it no longer represents anything coherent. But this endpoint is so far in the future, so many trillions upon trillions of years away, that it is almost beyond conception. The universe is currently young, active, full of structure and change. We exist in an era when galaxies shine, when stars are being born, when complexity is increasing locally even as entropy increases globally. This era will last for timescales that dwarf all of recorded human history. And during this era, we have the privilege of consciousness, of awareness, of the ability to contemplate these deep questions about what reality is. The holographic principle is part of that contemplation, a glimpse into the mathematical structure underlying the universe, a hint that reality is stranger and more beautiful than our everyday experience suggests. As we consider this cosmic perspective, the concerns of daily life naturally recede. The stresses and anxieties that seem so important become small against the backdrop of cosmic time and space. Not irrelevant, not meaningless, but proportioned differently, seen in a larger context where the ultimate fate of the universe is to dissolve into equilibrium. There is a kind of peace in this perspective, an acceptance of impermanence, a recognition that all structures are temporary, all patterns eventually fade. The holographic principle tells us that information is never lost, that it persists even as forms change, but it also suggests that information can become so dispersed, so randomized, that coherent structure disappears. This is the ultimate letting go, the cosmic version of falling asleep. The universe began in a low entropy state, highly ordered, full of potential. It has been evolving toward higher entropy ever since, structures forming and dissipating, energy flowing from usable to unusable, order emerging locally, but disorder increasing globally. Eventually, the universe will sleep, settling into a state of perfect rest where nothing changes because all change has been exhausted. And in contemplating this eventual sleep, we can find a metaphor for our own nightly rest, for the dissolution of waking consciousness into dreams and then into deep sleep. The universe, like us, moves toward rest. Patterns cohere for a time, maintain their structure, process information, and then gradually dissolve back into the background. This is not tragedy. This is the natural cycle, the rhythm of existence at every scale. Let your mind begin to release its grip on these ideas. The holographic principle, the emergence of space, the encoding of information on boundaries, all of this is fascinating and profound, but it is also just description, just mathematics, just one way of understanding what is. The reality itself, whatever it ultimately is, continues regardless of how we describe it. You are here, now, experiencing this moment. Whether that experience is best described as a three-dimensional pattern or a two-dimensional encoding or some other formulation we have not yet discovered, the experience itself is immediate and real. The weight of your body, the rhythm of your breathing, the quiet of the room, these are not diminished by being describable in multiple ways. They are what they are, direct and present. And as you prepare to let go of waking consciousness, as you drift towards sleep, you are participating in a small version of what the universe itself does on cosmic scales. You are dissolving structure, releasing pattern, allowing information to become less coherent, less organized, settling into a state of rest. This dissolution is temporary for you. You will wake again, consciousness will re-emerge, patterns will reform. But the mechanism is the same, the letting go of organized complexity into simpler, quieter states. Sleep is not the enemy of waking. It is its complement, the necessary counterpart that makes waking possible. Without rest, without the dissolution of pattern, there can be no renewal, no fresh coherence. The universe knows this rhythm, this cycle of forming and dissolving, and you are part of that rhythm. So as these words fade, as your attention drifts away from the questions of holography and information and the nature of reality, let yourself simply be. You are a pattern, yes, an information structure describable in multiple ways, but you are also just this immediate presence, this breath, this moment. And in this moment, nothing needs to be understood. Nothing needs to be figured out. There is only the gentle release into rest, into the quiet darkness that holds all patterns, all information, all experience. You are real, whether described holographically or three-dimensionally or in ways we have not yet imagined. You are here, whether here means a location in space or a pattern on a boundary or something else entirely. You are conscious, whether consciousness emerges from neurons or from quantum fields or from structures we cannot yet name. And right now, none of that matters. What matters is rest, the settling of thought, the quieting of questions, the dissolution of waking concern into the peaceful darkness of sleep. The universe will still be here when you wake. The holographic principle will still be true or false, or something more subtle than true or false. The boundary will still encode information. Space will still emerge from entanglement. The mathematics will still be beautiful. But for now, let it all fade. Let the three-dimensional world soften and blur. Let the boundary become distant, unreachable, irrelevant. Let the information that defines you remain, but let the processing pause, the patterns quiet, the structure rest. You are falling, not into a black hole, not across an event horizon, but simply into sleep, into the natural and gentle dissolution that comes at the end of every day. The holographic universe continues without your observation. The boundary encodes, The interior emerges. Space maintains its illusion of depth. Time flows forward in its mysterious way. But you do not need to track any of this. You do not need to maintain awareness. You can let go completely, trusting that the patterns that define you will persist, that information is conserved, that you will return when the time comes. And so you rest, not on solid ground, because solid ground was always just description, always just one way of organizing information. You rest in the pattern itself, in the structure of information that is more fundamental than any particular substrate. You rest in the mathematical relationships that define existence, in the quantum correlations that create space, in the eternal encoding on the cosmic boundary. Sleep now. Let consciousness fade. Let the questions dissolve. Let the world, with all its dimensions and descriptions and holographic projections, continue without you for a time. You have explored the nature of reality, glimpsed the mathematical structure underlying existence, understood that you are both more and less than you appear. You are a pattern in a holographic universe, a three-dimensional experience arising from two-dimensional information, a moment of coherence in the eternal encoding. And that is enough. That is everything. Rest now in the pattern. Rest in the projection. Rest in the beautiful, strange, holographic universe that holds you and everything else in its infinite information, preserved forever on the boundary of all that is. Good night.